Okay, so today we're going to be talking about nucleophiles and electrophiles. So this is a very, very important concept to understand in OChem because all reactions and all synthesis problems you may have are all based around nucleophilic reactions which occur to an electrophile. So simply, let's just explain what is a nucleophile. So a nucleophile is essentially, let's just draw example of a good nucleophile. It's a molecule that is electron rich. So we know this would have too many valence electrons, it would give it a negative charge. So this is let's just put a label on it. This is the nucleophile. And this is the nucleophile. Oh, let me do that. This is the nucleophile. You can just think of it as being electron rich. It has a negative charge and it wants to get rid of this negative charge that we have here. So how can it do that? It can do that by attacking electrophiles. So an electrophile, let's draw a example of that, would be, if you think just logically, if a nucleophile has a negative charge, we would assume a electrophile would have a positive charge, and you would be right. So that is the electrophile. So this electrophile has a positive charge. It does not have enough valence electrons to completely fill its shell. It has a positive charge, but the nucleophile has too many. So essentially, the nucleophile will say, hey, I'm negative. I want to get rid of my negative charge. Oh, look, we have a positive charge right here. Why don't I just attack this molecule? And that will occur. Oh, I need to get rid of this. That will occur, giving us a molecule that would look like this. So this reaction occurs, we would have this. Now the carbon, we have the hydrogens like before, but now we also have OH. There's no more charge. There's no negative, there's no positive. Oh, excuse me, positive, and it is happy. It is doing okay. So, in a question that you would get, this is a very simplified version of it. You can kind of think back to acid-base reactions. So here I have a very simple acid-base reaction. We know OH. This is an ionic bond, NaOH. OH has the negative charge, sodium has the positive charge, but it equals out, it has a net neutral charge. So it would react, so we can kind of just assume that the OH would take this hydrogen, making H2O, leaving chlorine to react with the sodium, giving NaCl. So that, if you completely understand that, if you're an OChem, you took Gen Chem, that is okay. But you may be thinking, well, how does that apply to nucleophiles? So let's draw a problem of a nucleophilic attack. And if you're wondering, I'm not going to go into SN1, SN2, E1, E2 just yet because that is a little complicated. Just jump right into that. So let's say we have bromine, this is going to be a SN2 reaction, but I'm not going to go into explaining what makes it SN2, SN1, E1, E2. And let's have it react with NaOH. So you're looking at NaOH positive. We know that. OH, that's the negative. So if you are given a problem that's saying what is the product here, OH, you can kind of just, if you see NaOH, you might be a little confused. Well, hold on, we have OH, now it's NaOH. You can really just assume this is going to be gone. This is going to be, OH is going to dissociate, it's going to become a negative charge, and you can just kind of throw away, at least mentally, just say, you know, this really doesn't matter. This is not going to be important until later on. So bromine and OH. OH, or not OH, excuse me, bromine right here is a good leaving group. Good leaving group is the easiest leaving groups to know are halogens like bromine, iodine, chlorine, and also fluorine. You're not going to see fluorine as much, but mainly just bromine, chlorine, and iodine sometimes. These are really good leaving groups because if you look at the periodic table, I don't have it with me right now to show you, but bromine is on the right-hand side, and it is very electronegative, and it wants to be alone. It is happy being alone with this negative charge because it wants 7 valence electrons, so it already is electronegative, so it's kind of okay just leaving let's draw this direction. Bromine will be leaving from this pentane, giving us, so bromine would just leave on its own, and it is chilling. It is happy to be here on its own. So bromine would leave. Already bromine would leave. And then, so we know carbocations, and bromine leaves, this would, if it did leave, that carbon would now have a positive charge. So OH, which is a nucleophile, says, ooh, this is an electrophilic center. I'm nucleophilic. I want to get in there and take bromine's place. I don't want my negative charge. Bromine's happy to have its negative charge. I'm gonna get in there and get rid of my negative charge. So the product would be looking like this. OH is now replacing bromine, and if you did have to draw the Na, you could just kind of assume it would be NaBr, but that really is not going to come up very often. So I would just kind of not worry about that right now. So if you are wondering, this is an SN2 reaction. And I said I wasn't going to go into it, but I guess I should explain. SN2, SN1, SN2, the easiest way to think about it, SN2 occurs in one step, while SN1 occurs in two distinct steps. So bromine leaves, and OH immediately takes its spot. It says, let me be in there. And it exists. Like the second bromine leaves, OH is already there. It's already replacing it. And there we go. And just so you know, since this is an important thing to understand, if bromine was a wedge here, it was a wedge, OH would now be a dash. Due to the nucleophilic backside attack, we invert the stereochemistry of the leaving group in the nucleophile. So if it's a wedge, it's a dash. If bromine was on a dash before, it is now on a wedge. So that is just essentially a quick rundown of what a nucleophile and electrophile is. Please let me know if I messed anything up or if I could explain something better. I am still an undergrad student, so I don't know everything, but please let me know what I got wrong in the comments.